If you have any interest in physics, you've probably heard that there's an idea kicking around in cosmology called inflation. But you may have no idea what it means. What does a word ordinarily associated with the economy have to do with physics? So let's talk about the idea. First, we'll talk about what it means and why it was invented, and then we'll talk about whether you should believe it or not. So, to start with, we need to know a couple of things. We begin with something pretty obvious. Space is big. So you might wonder just how big it is. Well, there are many ways to say it, but I kind of like how Douglas Adams said it in The Hitchhiker's Guide to the Galaxy when he wrote, and I'm paraphrasing a bit here, "You may think it's a long way down the road to the market, but that's just peanuts to space." Although, even that may not convey the complete truth. The point is that space is really big. The second important point is that when we look out into space, as far as we can see, space is uniform when we view it on the biggest scales. Look to your left, and then look to your right, and it looks the same. Let's combine those two ideas and see why scientists are so puzzled. We'll do this by jumping into space. So here I am in the middle of outer space, and I'm going to clone myself twice and send the clones back in time to the beginning of the universe and as far away as it is possible to see. How do I do that, you ask? Good special effects team. So, if I turn to my right, I can see light from my clone sent when the cosmos began. Light emitted about 14 billion years ago. It's just getting here now. Thanks, Guy. No problem. Similarly, if I turn to my left, again, I see light arriving from my other clone, sent just after the Big Bang. Thanks to you too. Sure. Now we get to the crux of the problem. Light from this guy is just getting to me now. It means the light hasn't had enough time to have gotten to him. Similarly, light from this clone hasn't made it to the clone over there. Because of this, the clones don't know about each other.
Know about who?
Exactly. Too many voices here. Maestro, can you get rid of these extra guys and maybe get me back on Earth? Thanks. So, this is the real point. The two sides of the universe that we can see have never been in communication with one another. But if they haven't ever been in communication with one another, how can they be so similar? Ordinarily, for two things to be similar, they have to be in contact long enough for things to mix together. We can see an example using this water and food color. We can put in a red drop and a blue drop separated from one another. These disturbances to the water make the two spots very different. However, if we wait long enough, the food color disperses and we get uniformly colored water that is purple everywhere. That's the key point. It takes time and contact for a medium to become uniform. It's the same in the universe. It's hard to understand how the two sides can look so alike given that they've never been in communication. Or have they? In order to solve this problem, in 1979, a brilliant physicist by the name of Alan Guth came up with an idea called inflation. The brilliant guy is the one on the right. Inflation is an extension of the basic idea of the Big Bang. Some of us would say that it's now an essential component. When the universe was much smaller than it is now, it was much easier for all of the bits to mix together and for the environment to become uniform. Guth's crucial idea is to imagine that after the universe became uniform, it grew incredibly quickly, thus locking in the uniformity. While the exact numbers are not yet confirmed by experiment, the idea is that at a time of about 10 to the minus 37 seconds after the Big Bang, the universe began to grow, doubling every 10 to the minus 37 seconds. So, in the first 10 to the minus 37 seconds, the universe doubled. In the second, the universe was 4 times its original size. In the third, the universe was 8 times bigger, and so on. This progression of 2, 4, 8, 16, 32, etc. went on for a minimum of 100 doubling periods. Now, it might have gone on for more than that, but for Guth's idea to explain the uniformity of the universe, it had to undergo at least 100 doubling periods. taking this minimum over the period of 10 to the minus 37 seconds to 10 to the minus 35 seconds, the universe expanded 2 to the 100 times, or about 10 to the 30 times, or a million trillion times. In that period of time, the universe went from the size of about a billionth of the size of a proton to about the size of a marble. After that, the crazy fast expansion of the inflation stopped, and the universe expanded in the ordinary way that we usually mean when we talk about the Big Bang. So, there are a couple of questions people have when they hear this idea. The first is they want to know how fast the expansion was. That's easy to calculate. If we take the size of a marble to be about a centimeter, we can divide that by the expansion time, which is about 10 to the minus 35 seconds. And we find that the average speed was 10 to the 33 meters per second, which is outrageously bigger than the speed of light. Since we've all heard that you can't go faster than the speed of light, this sounds like a nonsensical prediction. However, we must be careful about what we know about relativity. The theory says that nothing can go through space faster than light, but it says nothing about how fast space itself can expand. So this superluminal expansion of space doesn't conflict with relativity at all. The second thing is perhaps even a bit weirder. When ordinary matter expands, the total amount of matter stays the same, although the density drops, as symbolized by the measured quantity on the scale on the left not moving and the balloon becoming more transparent. However, this isn't true of the energy of space. When space expands, it seems that the energy density remains the same. So if the energy density remains the same and the volume gets bigger, that means the energy gets bigger. This is demonstrated symbolically on the right-hand scale by a constant color and a changing mass. One of the fundamental tenets of physics is that energy is conserved. So this sounds like a very bad, perhaps even fatal prediction. However, there is a saving fact. Not all energy is positive. It's possible to have negative energy, and gravity involves negative energy. Further, as the universe expands, there is more gravitational energy. Thus, the energy that is created in the expansion of the universe is offset by the increased gravitational energy. In this way, a universe with zero initial energy could expand and not break the energy rules. So I've described the core ideas of inflation, but there are lots of ideas in cosmology, and some of them are just that, ideas. But they just don't describe our universe. Well, is inflation real? The simple answer is we just don't know. In 2014, the BICEP2 collaboration announced that they saw polarization patterns in the cosmic background radiation patterns from deepest space that were consistent with the theory of inflation. However, a follow-on measurement by the Planck collaboration showed that at least some of the initial signal could be explained by dust in our galaxy. The two experimental groups are talking to one another to try to get to the bottom of things. This sort of ebb and flow of data and ideas is how science works, and eventually the groups will figure it all out. Thus, the idea of inflation has not been proven, but the idea is consistent with all known measurements and is the leading contender to explain the uniformity of the universe. Now, no matter how much we want to know the answer right now, we're just going to have to wait to find out if the data supports the idea or rules it out. Welcome to my world.